All right. We are going to see a little bit of a change of pace now. So far, we've been studying kinematics for the last unit and quite a few segments. At this point, we're going to go on to another important component of our overall development of continuum mechanics. We're going to go to balance laws. Okay? So we'll start there. So we're now going to start the topic of balance laws. And you may recall from one of the very first segments, or you could go back and look at that segment, we talked about the following balance laws, right? We talked about the balance of mass, we talked about the balance of momentum, and when we talk of balance of momentum, we talk about two types of momenta: the balance of linear momentum and this is essentially our continuum representation of Newton's laws of motion. Okay, this is this is what the balance of linear momentum is. And then we also have the balance of angular momentum. So maybe I should call this 2A, and then we call this 2B, is the balance of angular momentum. Okay. Now, just as the balance of linear momentum is our version of what Newton described, the balance of angular momentum is often credited to Euler. Okay. So this is basically 2A is essentially Newton's laws. Okay. And this is Euler's laws. Of course, you note that whenever we talk about anything ascribed to either Newton or Euler or Cauchy or other people like this, we need to be very specific about exactly which of their contributions we are talking about, right? So this is what we mean here. All right. And then the third balance law that we will also look at is the balance of energy. Okay. The balance of energy is what gives rise eventually to things like the heat equation. Okay. And to complete this, I should probably also mention that the balance of mass, very first of these, is what gives us things like this is the framework in which things like fixed laws of diffusion are posed. Okay? So we may look at this as, let's just talk about, well, it's, let me just say things like diffusion here. Okay? All right. So of these, we'll start at the top. We are going to start with the balance of mass. Okay? So we'll talk about the balance of mass in the continuum setting. Okay? And in the setting of continuum mechanics. Okay? By which, you recall, we mean that we are not looking at things discretely, right? We're not going to look at particles going in and out of some volume, but really look at this in a continuous sense. Okay, so one thing to note is that we don't really try to we don't do anything like trying to derive the notion of mass from anything else. In continuum mechanics, mass is a primitive concept. Okay, so the idea of mass is a primitive concept in continuum mechanics. Okay. One way to think about it is to go to Newton's description of gravity and observe that mass is that quantity which leads to a force between two objects, right? In the absence of any other kind of force field that we know about, right? So, so in the context of Newton's laws of gravity, right? In the context of Newton's laws of gravity, a mass m, okay, and another mass capital M, okay, are sort of characterized by the fact that they have a force between them, right? They are characterized by their, and in this case we are interested in their gravitational force, right, which is that the force due to gravity is, how should I write it? Let's write it as F here. F equals G being the universal gravitational constant, m over r square, okay, in the direction E, right, where E is a vector joining the two masses. Okay, and then of course depending upon which mass you're sitting on and what and how you're defining the force of attraction acting on that mass, you would choose E, right? So if you have a little mass m, you have another mass here m, right? If you're looking at the force as acting on the little mass m, you would describe the vector E to be that one, in the sense that this mass is being attracted toward the other one. Okay? All right, this is sort of standard notion, right? And then from here, of course, we observe that if m is something like the mass of the Earth, then we just rewrite this as, if m is the mass of the Earth, r is its radius, right? And then the picture is that this is the Earth. We have a little mass sitting on top here, m. This entire mass here is capital M, right? And then we say that the radius between them is that, right? That is the radius of the Earth. Okay? And in this case, we write F equals mg, right? Where in this case, going back to the previous equation, we see that g is the vector g m over r square e, right? Just to put everything in context. And of course, in this setting, we say that g, we often treat little g as a constant, right? We all know about this. Okay, so this is the mass that we're talking about. Of course, I've done this in the case of two discrete masses, right? Little m and capital M. Okay? And the whole point is this is not how we want to treat it in continuum mechanics, right? We want to do something different. Okay? So, in the continuum mechanical setting, the mass is going to be characterized by a continuous function, which is the mass density function. Okay? So, in continuum mechanics, okay, we use the mass density function. Okay, and as is common convention, we will denote it as rho. Let's denote a particular mass density as rho naught. It's a function of reference position. Okay, and what we have here is the following idea. This is the body in its reference configuration. Okay, we're saying that this body has a mass density, which is a function of position. Okay? Okay? So, in continuum mechanics, we use the mass density function rho 0, right, which is a continuous function of the reference position. Okay? All right. Now, the idea is that our mass density function remains continuous regardless of the severity of the deformation. Okay, we know that now we can actually talk about the severity of the deformation by looking at our strain measures, which we've defined, right? And we've also defined strain rate measures, right? So using those, we may talk about how severe or how extreme the deformation is. And the idea is that regardless of how bad the deformation is, how severe it is, our mass density function remains continuous. Okay, so actually let me put that down. So the idea is that rho 0 function of x remains continuous regardless of the deformation. Okay, and what we mean by the deformation is that what we mean is that you could consider the deformation gradient f. You may construct some sort of norm of it. You may construct a Euclidean norm of the deformation gradient, or you may do that with the Lagrange strain E. E, of course, implies all the stretches and so forth. You may even do it in terms of the velocity gradients, right? You may even do it in terms of that quantity, right? Right, or anything else. Regardless of what we see about those quantities, how big they are, in a sense, how big their norm is, we will insist that the density, the mass density, remains continuous. Okay? What that means is that in the context of a solid body, right, we are saying that, well, if this is the reference configuration, I really don't care about how bad that deformation is, things remain continuous, right? Likewise with the fluid. And this is important, okay? In the context of the fluid, let me make sure, okay, so you can see the window. In the context of this fluid as well, things remain continuous, right? I may shake this up, and though you're probably seeing some bubbles being introduced, right? That is the phenomenon of cavitation you're seeing in that fluid. Okay, that makes the fluid turbulent. You're probably seeing some bubbles, some cavitation. The point is that in our elementary entry-level treatment of continuum mechanics and the continuum mechanics of fluids, we are not treating cavitation. Okay, there are ways to treat cavitation, but we're not going to get into it right now. Okay, so the standard treatment of continuum mechanics can be extended to treat cavitation. Okay, likewise in this context, right? In the context of a solid body, also we say that regardless of how extreme the deformation is, right, things remain continuous. Now, just as in the case of the fluid, we saw that under extreme types of flow, extreme turbulence, cavitation happens, right? We form bubbles where obviously the density goes to zero. The same sort of thing does indeed happen in solids. If you think of this as a polymeric material, and yes, it's a foam, but think of it as a continuous polymer, it is known that most polymeric materials, at least soft polymers, admit cavitation under extreme modes of deformation. So if you were to take this and really start pulling it apart, polymeric materials do finally start forming voids inside of them. The same thing happens with metals under extreme rates of deformation. Both type of materials and others also fracture, right? Which is also a loss of the density going to zero. If you now imagine a crack going through this, then well, the body comes apart, and in that region you have zero density of the solid, right? And then the density is also not continuous, because if you think of a crack forming, you have density continuous up to some point and then discontinuous, right? It goes to zero discontinuously, right? We are not going to consider those types of deformations in this entry-level treatment of continuum mechanics. Continuum mechanics can indeed be extended to treat the case of cavitation in fluids, as well as void formation or the formation of cracks in solids, and that's been done, right? But we won't go there. Okay. So we have the statement that rho zero remains continuous regardless of the deformation, and observe that I've written rho zero parameterized by reference position, and likewise just recall that x and t in general parameterize the deformation gradient, right? So what we're saying is that if at that point, capital X, right, the deformation gradient takes on a certain value, right? Right, and the body may be really deformed, right? Okay, and that may be our point little x. Okay, which is obtained from capital X here. Okay. All right. Nevertheless, we say that the density of that point remains continuous. Right? Okay. All right. So this is an important notion. Okay. There are one or two things I should say about the mass density parameterized by the reference configuration. Okay. We can talk of rho zero function of x could be a constant, right? So let me just denote that as maybe rho zero bar constant. Okay. When this happens, what we are saying here is that the mass density is not a function of position. That is roughly the case with this solid body. Okay? The density is pretty much uniform throughout the body, and that is the situation I've written out here. Okay? So when this happens, we say that the body is homogeneous. Okay? The body is homogeneous in its reference configuration.